quick video on stuff that we did do in class, but I want to show you just a few more examples that can be challenging. A little more interesting factoring stuff than the absolute basics. The tools grouping is very powerful, either for like quadratic trinomials sometimes or more complicated stuff, works for some cubics. Have your perfect square trinomials memorized and be able to recognize those. That's very, very useful. Difference of squares is so powerful. Just you can get a lot of great stuff out of difference of squares. And difference of cubes is a thing as well. When you have a difference of cubes that factors in a way that's really rather like difference of squares, just a little more complicated. You've got this plus AB. And the very cool thing is that a sum of cubes factors as well. The minus signs switch. It's plus in the binomial and a minus in the middle of the trinomial. Sum of squares, no, doesn't have a factorization unless you go and use imaginary numbers. Okay, so using some of those tools, let's see how to do some of these guys. It's a cubic. It's got a constant term here, so you couldn't just factor out an x or an x squared, which you sometimes can with simpler examples. The only tool that we have, it doesn't really fit this because it's definitely more complicated than these guys. So the only tool we have for sort of general cubic like that, with a cubic term, a squared, a linear, in other words, x to the first, and a constant term, is we're going to hope that the grouping applies. Well, okay, and so that means let's group these first two together, factor out anything we can, and we get 3x times x squared minus 4. Okay, all right, now let's look at the other two and hope that this works. Hey, if you factor 5 out of here, this is nice. And so now it's, that's a x squared, my bad. The x squared goes here. Hopefully you noticed that, but you might not have. I factored a 3x squared out of here, and this is x minus 4. Otherwise, this would have totally not worked. But we factored out a 3x squared and an x minus 4, 5x minus 4. Okay, so now x minus 4 is a common factor, and it's being multiplied by both 3x squared and 5. And we've got a factorization. You always want to ask yourself, does this go any further? Ooh, this is most looking like a sum of squares. It's not going to factor any further than that. So that's as good as we can do. Okay. So, all right, I'm glad I've already made a mistake that I corrected. It's always good to demonstrate that. Yay. Okay. What about this one? We don't have anything that specifically talks about 8th powers and 4th powers. But this actually does fit into this pattern, as long as we recognize that this first term, it is the square of something, and the second term is the square of something, just something interesting. This is the quantity 9x to the 4th squared, and this is the quantity 4y squared squared. Okay, so this is so powerful that these patterns apply to any number a and any number b. It applies to any letter instead of a and instead of b, but most powerfully it applies to anything at all that is some expression that defines some quantity squared, and that itself can be something interesting. Okay, so now that's going to be 9x to the 4th plus 4y squared times 9x to the 4th minus 4y squared. Here, it's looking like a sum of squares. Even if we're clever, it's looking more like a sum of squares. And indeed, it is a sum of squares. That doesn't factor further, but this does. That's exactly, again, a difference of squares. So we're just going to copy that. There's nothing we can do with that. This 9x to the 4th, let me just rewrite it. Right? This is 3x squared squared, and then minus the quantity 2y squared. Notice the huge difference between 4y squared, right? The order of operations says do the square first and then the 4. This is saying I can put the parentheses differently, but this has to be a 2 because this is going to square the 2 and square the y. Okay, so now that's a prep step, and now this is going to be 3x squared plus 2y and 3x squared minus 2y. Okay, that's about as good as we can get, because it's none of these are one of our nice patterns. And that's as full of factorization as we could get for that. So we didn't use anything super clever or obscure. We just used difference of squares, but we did it in an interesting context. All right, so I'd say that's sort of medium difficulty. What about this one? It's going to be, um, we're going to be able to factor some stuff out of this. Oops. Let me just, sorry, it's not happy. Okay. Let's see. I can just factor a numerical factor out of this, and I can factor an x out. So let's take the 7 and the x out, and then I get 4x squared minus 1. Okay, so we've already made progress. It was a cubic. Now we got it as just a linear, a real simple linear number times x times a quadratic. It's already progress, but if we want to fully factor, we recognize, hey, again, it's a difference of squares. We just love those difference of squares. 2x plus 1, 2x minus 1, right? Because the 4x squared is the quantity 2x all squared. So I'm just doing it a little quicker there. This is a very common thing that fundamentally the tool, the big tool we're using is difference of squares, but you might be surprised by this. Like, wait, where's the squares? This is not a square number. That's not a square number. That's not an even power. Oh, okay. When we factor out this easy factor of 7x, what's remaining is a difference of squares. Okay, so moving on pretty quickly here. Now, what about this one? Okay, now this is cube. I don't have an x here, so it's rather different from the previous one. I can't factor out any x's out, so this is going to stay a cube. But I can factor out a numerical factor. Okay, so let's copy and paste that. And I get something that's suggestive. Oh, 8. Oh, that's kind of nice. Let's rewrite that. That's 2x quantity cubed plus 1. Aha. And that's where we do have a formula. Even though it's a sum, it's going to be 2x plus 1. Right? So let's go back up to the pattern here. I'll even copy it back down. This is the sum of cubes pattern. And we'll remind ourselves just like right here. Okay, so the a is 2x, the b is 1. So it's going to be a plus b. And then a squared, that's going to be the quantity 2x all squared, or I'm going to write it as 4x squared minus 2x plus 1. Okay. Okay, so we had to factor out a 5 to see that. We had to deal with the 2 here, work that correctly. That's definitely a little more challenging. Okay, and now as a contrast, or just a little addition to that, this is very, very similar, but it's just got one more thing added into it. Whoops. That this one does have some powers of x that we could take out. Right, so this one, if we saw this, it'd be really very similar. We can take out a 5, we can take out an x squared, and then we just get exactly the same examples before. Okay, so that's going to be super, super similar. I'm even just going to copy and paste. So just to make the point that sometimes when you have powers that are sort of higher than you're used to, a degree of a polynomial that's higher than you're used to dealing with, that might not actually be the key thing. If every term in your polynomial has some decently high power of x, the first thing you might be able to do is factor that out, and then it might reduce to something a bit more familiar.